Okay, we're gonna do We're gonna just do the discharge. This is part 3 of capacitance, and we'll just do the discharging, and then we'll be done capacitors. So capacitor discharge. It looks like this. When you, and this is going to happen when you, if you have a switch or you turn off the voltage that's pushing the charge onto the capacitor. If it's already stored in the capacitor and you just close the switch in the circuit, it will come out. And this is how that one team got their solar power car to work. Do you remember that?
No.
I really want to build that still.
We should.
They stored it up on the capacitor and released it so the car would roll. It wasn't enough current to make the motor turn on its own, right? The panel. But they stored the energy on the capacitor. And then they used, it wasn't a transistor actually, it was called a thyristor. And it stored the charge and then released it. So it would move and then stop and store and then move and then stop and store and move.
Got 2 months free until I fly out. So
say that again?
I've got 2 months free until I fly out.
You have 2 months free.
After
We're gonna build that. We're gonna build that. You start at, so this is voltage versus time this time, and you start at whatever your V naught is, and it's gonna look something like this, and the relationship is V equals V naught. And what do you think comes next, looking at that graph? Very similar to a nuclear decay graph.
Oh,
E. Yeah. Kenta, say it again.
Power to negative t over the time constant.
Yeah, over RC. And we can say that this, we use tau to equal RC, and as Kenta aptly points out, the tau is the time constant.
Give them the time constant. We're giving the formula. No, we're giving the time constant. Oh, we're giving RC.
So let's do a little example. Let's say you have a capacitor. I'll draw the plates here, and you got a switch in it, and it goes. There's a little. Oh, I'm sorry. Draw that little circuit on your page. Let's say this is a 5 ohm resistor, and let's say we start with 10 volts. I should have drawn a cell in here or something, but let's say we start with 10 volts and it's going to discharge to 2 volts. And our capacitance, let's say, is 3 microfarads. And the question is, how long does this discharge take? Yeah. Sorry. So what are we gonna have to do to this?
Long.
You're gonna have to lawn it.
I love long.
So you get your V naught under here, and you're gonna have 10 over 2, so that's gonna be 5. And, or sorry, that's 2 over 5, and you're gonna have 0.2. But you're gonna lawn both sides. And you're going to end up with this is going to come down. You're going to end up with T being equal to negative RC ln V naught. I think if you do that all out, I think that's what you get. And if you calculate that, well, I should have, I don't want to tell you. It's, do you have it done, Colin? You don't have a calculator? Did you do it?
No. I don't know if I did it correctly.
Should we say the answer?
Yeah, I think that's correct.
What's the answer?
2.41 times 10 to the negative 5 seconds.
Golf clap for Ben. 2.4 times 10 to the negative 5 seconds. This happens, whoa, this happens pretty quickly. So this would be 24 microseconds. Not very long at all, but that time does matter. Can somebody remind me when we do, at some point in the regular class, I need to do AC current and RMS voltage and like rectifiers, full bridge rectifiers. This is used
Rectifiers.
in full bridge rectifiers.
And transformers.
Has anybody got a list going of what we need to?
Rectifiers, transformers,
I can stop